friends. In this video, we are going to study about the design specifications in frequency domain. Whenever we want to design any control system in the frequency domain, then these specifications have to be specified by the manufacturer. So let's study about these specifications. We know that when we study the control system, we study the systems in two domains. One is the time domain and second is the frequency domain. In time domain also, we have some specifications which are known as the transient specifications of the system. Just like the transient specifications, the control system also have some specifications in the frequency domain. Okay, so these specifications are necessary whenever we want to design the system in the frequency domain. So the first design specification is the resonance peak. Now, this is the block diagram for a closed loop control system, and the transfer function of this system, which is the ratio of the Laplace transform of output and the input, that is Cs upon Rs. It is given by Gs upon 1 plus minus Gs Hs. So this is the transfer function. Now if we want, this is the transfer function. So now if we want to convert it into the frequency domain, we have to replace this S by j omega. So C j omega upon R j omega. This is the transfer function in the frequency domain. We have replaced S by j omega, so it is converted into the frequency domain. Now if we take the magnitude of this transfer function, which is represented by the two lines here, this is the magnitude which we have taken. So it is represented by m j omega. This is the magnitude of this transfer function. So this mj omega, it is called the maximum value of the magnitude or the closed loop frequency response, because we have written this is a closed loop system. We have written the transfer function of this. So this is a closed loop transfer function. Then we converted into the frequency domain. So this has become the closed loop frequency response of the system. So this mj omega, it is the maximum value of the mj omega or the magnitude of the transfer function. So we call this as the magnitude of the closed loop frequency response, and we can say this is the resonance peak MR. This resonance peak, this specification is useful to define the relative stability of the system. Okay, and its value, it ranges from 1.1 to 1.5. So this is the resonance peak, the first specification in the frequency domain. Now next specification is the resonance frequency. Just like in the transient specifications or the specifications in time domain, we studied the maximum overshoot. So here we have the resonance peak. Maximum overshoot was also the maximum value which is attained by the system. So here also the resonance peak, it is the maximum value of the magnitude or the closed loop frequency response. Next we were having damping frequency and natural frequency. Here we are having the resonance frequency. So the next specification is resonant frequency. So resonant frequency, it is the frequency at which the resonant peak occurs. That is MR, the frequency at which the MR is occurring. That frequency is called the resonant frequency and it is represented by omega R. Now this resonant frequency, it gives us information about the speed of the transient response. That is how fast the speed or how fast the response of the system is. Because if the resonant peak is occurring at a very less time, like when we have started the system and within 10 seconds the system is reaching to its maximum peak or maximum magnitude, it means that the speed of the system is very fast. So this resonant frequency, it is giving us information about the speed of the transient response. That is how fast the system is attaining its maximum value. Okay. Now the next specification is bandwidth. So bandwidth is defined as the range of frequencies for which the system gain is more than 3 dBs. 3 dB we have defined a value for the magnitude, and if the system gain it is reaching more than 3 dB, so that range of frequency is called the bandwidth. Okay. Now bandwidth or this range of gain, that is when the gain is more than 3 dB. So this range ensures that the signal is properly transmitted. Okay. Now if the bandwidth is large, then higher frequencies will pass through the system, and this passing of the higher frequency, it is an indication of faster rise in time. So bandwidth is giving us the proper transmission, it is ensuring us that the signal is properly transmitted, and also if the bandwidth is large, then it also indicates that the rise in time is also fast. Okay, that is rise time is fast, is large. So this is the third design specification in the frequency domain. Next we have cutoff rate. So next is specification is our cutoff rate, and it is the slope of the log magnitude curve near the cutoff frequency. When we draw the magnitude curve, because in frequency domain, whenever we draw the curve, we use the logarithmic plot for it. So the log magnitude curve, we are taking the log of the magnitude, and the slope of that curve near the cutoff frequency is called the cutoff rate. Now, the ability of the system to distinguish a signal from the noise, okay, means when the signal, it can be disturbed by other unwanted signals, and those unwanted signals are called noise. So whether the signal which is given to the system, it is the proper input signal or it is a noise, that to differentiate between the signal and the noise, this cutoff rate is important. So using this cutoff rate, the system can distinguish between a signal and a noise. Okay. Now, next is specification is phase margin. So phase margin, it is defined as the additional phase lag at the grain crossover frequency required to bring the system to the verge of instability. Means every system will have some phase lag with it, some phase associated with it. Okay, so for this phase lag means the difference between the standard phase and the phase which is the system is having. So this is the additional amount of phase lag which is present at the gain crossover frequency, which the system requires so that the system can be bring to the verge of instability. Okay. Now here we have another term, gain crossover frequency. So let's define it. The gain crossover frequency. So the gain crossover frequency, it is the frequency at which this magnitude Gj omega, which is known as the open loop transfer function. When we calculate the transfer function of a system, then Gj omega comes out to be the open loop transfer function, and the closed loop transfer function is Gj omega upon 1 plus minus Gj omega Hj omega. That was the closed loop transfer function. Now, open loop transfer function magnitude, that is mod of Gj omega, when it is equal to unity, means it has attained its maximum value, then that frequency is known as the gain crossover frequency. And when the magnitude is unity, that is at the gain crossover frequency, the additional phase lag or the phase that the system is missing, that additional phase lag which the system require to bring it to the verge of instability is called the phase margin. Okay, and the formula for this phase margin, it is given by 180 degrees plus phi. Okay, and this phi, it is the phase angle of the system at the gain crossover frequency. Okay, so this is the phase margin. Now next is specification is gain margin, and both these specifications, gain margin and phase margin, are very important whenever we are describing the system in the frequency domain. So gain margin, it is the amount of gain in dBs, that is decibels, that can be added to the open loop transfer function before the closed loop system becomes unstable. Just like phase margin was the additional phase lag which have to be added to the system so that it can be bring to the verge of instability. Here also gain margin, it is the additional amount of gain in decibels which can be added to the open loop transfer function so that the closed loop transfer function cannot become unstable. Okay. Now there we studied the gain crossover frequency. Here we have the phase crossover frequency. Okay. So phase crossover frequency is the frequency at which the phase angle is minus 180 degrees, and gain crossover frequency was the frequency when the gain was 1, that is unity. Okay, so that's the difference between the gain margin and the phase margin. Now the formula for the gain margin is minus 20 log magnitude of Gj omega. Okay. Now, these phase margin and the gain margin, they also defines the stability of the system. How? Let's see. If the system is having a positive gain margin and a positive phase margin, then the system is stable. If it has negative gain margin and negative phase margin, then the system is unstable. And if it is having zero gain margin and phase margin, then the system is marginally stable. Let's see how stability is it. Let's write. Okay, so how the stability is defined by gain margin and phase margin. If positive gain margin is there, then system is stable. If negative gain margin is there, then system is unstable. And if both gain margin, phase margin are zero, then the system is marginally stable. Let's draw that the gain margin and phase margin, when we draw the Bode plot for the system, how they can be calculated. So you can see here that the plot of the magnitude with response to frequency, and this is the phase plot with response to frequency. So here we have the positive gain margin, and here also we have the positive phase margin. Okay, so whenever the system is having positive gain margin and phase margin, that system is a stable system. Now if we see the Bode plot for the unstable system, so in this you can see that this is the plot of the magnitude in decibels, and this is the phase angle in degrees. And this line is for 0 dBs and this line is for 180 degrees. Okay. So this is the negative gain margin, and here also we are getting the negative phase margin. So this is the Bode plot for an unstable system. So you can see that how the design specifications are very important when we are studying the nature of the control systems in the frequency domain, and how these specifications define the stability of the system. So we have studied the specifications in the time domain also. Earlier we have studied the transient specifications, and now we have studied the design specifications in frequency domain. So how we can correlate the time domain and the frequency domain? Let's see it. So what's the need of it? There are sometimes that we have defined the system in time domain and we want to study its nature in frequency domain also. And there are some systems which can be easily described in frequency domain but not in the time domain. So if we can correlate both the frequency and time domain, then we can study the nature of the system in both the domains. So let's study the second order control system first, because we know the response of it. So for a second order control system, so here we have the transfer function of a second order control system. This is the generalized transfer function in the time domain. Now this here we have considered that the HS, the feedback loop, is unity. It is having a unity feedback loop system. So the GS is equals to omega n square upon S square plus 2 del omega ns plus omega n square. Now we know that whenever we want to convert a system from time domain to frequency domain, we have to just replace this S by J omega. So here wherever we have S, we will write J omega, and then this transfer function can be converted in the frequency domain. So it will become G J omega. This is omega n square. S will be replaced by J omega. So this we have got here. Now if we take the square, that is J square omega square, then it will become, J square is what? Minus 1. So it is minus omega square. Now take omega n square common. Okay. And then omega n square will be cancelled from the numerator. So we will have here omega n square. So we have taken the omega n square common. So this will become 1. It will become 2 del j omega upon omega n, and this will become omega square upon omega n square. Okay. Now this omega n square and omega n square will be cancelled. So we are getting g j omega. Okay. Now if we take omega upon omega n as another variable u, so let u equals to omega upon omega n, then this expression will be changed into So we have just taken this omega upon omega n as another variable u. So this transfer function we have obtained. Now we are going to take the magnitude and the phase angle of this transfer function. So magnitude will be magnitude we have taken. So magnitude will be real part square minus imaginary part plus imaginary part square and under root. So real part is 1 minus u square. So we have taken the real part square 1 minus u square whole square plus the imaginary part is 2 del u. So 2 u del square. Okay, and phase angle is minus tan inverse of imaginary part upon the real part. So this is the magnitude and phase angle of this transfer function. So we have calculated the magnitude and the phase. Now in the frequency domain, we have studied the design specification as the resonant frequency. So here we are going to calculate the resonant frequency. So to determine the omega r, to determine the resonant frequency, we have to differentiate this gj omega with respect to u, and then we have to equate it to 0 and replace this u by ur. So what we are going to get when we are going to differentiate it, then we will get ur equals to under root of 1 minus 2 del square. Okay, and this ur, because we have taken that u equals to omega upon omega n, we have taken the variable omega upon omega n. So here omega was our frequency, so this ur will be resonant frequency upon omega n, that is the natural frequency. So we will write ur as omega r upon omega n equals to under root of 1 minus 2 del square. That means it is the ratio of the resonant frequency and the natural frequency. Now natural frequency, we are defining it in the time domain. In transient specifications, we have studied the natural frequency, and omega r is in the frequency domain. So we have got the relationship between the frequency domain and the time domain. Okay, that is, we are relating the resonant frequency with the natural frequency. Now if we say omega r will be equals to omega n under root of 1 minus 2 del square. This is the relation between the resonant and the natural frequency. Earlier also, when we have studied the transient specification, we know that omega n equals to omega d equals to omega n under root of 1 minus del square. This is the relation between the damping frequency and the natural frequency, and this relation is between the resonant and the natural frequency. Now another specification was resonant peak. So when we calculate resonant peak, it comes out to be 1 upon so this is MR, that is resonant peak, which is equal to 1 upon under root of 4 del square and multiplied with 1 minus del square. If we simplify it, it will be 1 upon 2 del under root of 1 minus del square. Okay, and we have maximum overshoot in the time domain also. So in this way, the frequency domain and the time domain are correlated with each other. You can see that the resonant peak is also a function of del, which is the damping ratio, and the resonant peak, it is also a function of the damping ratio. Now from these things we can get that the phi r, which is the phase angle of gj omega when u is equals to ur. So this is the phase angle, or we can say the resonant phase when the gj omega at u equals to ur. So this comes out to be minus tan inverse of under root 1 minus 2 del square upon del. The difference is only that of this two factor between the time domain and the frequency domain. So we have various results based on it, and the first is that as del approaches 0, so we have different ranges for defined for this del, because omega r is also a function of del and mr is also a function of del. So you can see that when del is equals to 0, omega r is equals to omega n. That is when damping ratio becomes 0, resonant frequency and natural frequency are equal, and the mr, it approaches infinity. Okay, now when the del is between 0 and 0.5, then omega r is less than omega n, and the mr, that is the resonant peak, it is greater than 1. Now when this del is greater than 0.707, the slope of the magnitude curve, it does not become 0 for any real value of omega. So you can see that the value of the mr and the omega r, that is the design specifications in frequency domain, resonant frequency and the maximum this resonant peak, they are how they are related with the damping ratio and the natural frequency. So this is how the correlation can be developed between the frequency domain and the time domain. So in this video we studied about the design specifications in frequency domain, and then we saw the correlations between them. So I hope that this video is clear to you. Thank you.